A neuron is part of a larger neuron network. To show this network, there is an ABC network that we created in class. You can see that the axon terminal buttons reach towards the dendritic authorization of the next cell. The axon terminal buttons are separated from the dendritic authorization by a space called the synapse. An event happens in cell A that causes neurotransmitters to be released in the synapse between cell A's presynaptic membrane and cell B's postsynaptic membrane. 4 things can happen to these neurotransmitters. 1. They can dissipate into the interstitial fluid. 2. They can be metabolized by ions in the interstitial fluid. 3. They can go back into the cell A through the process of reuptake. And 4. They can bind to the binding site of the receptor cell of cell B's postsynaptic membrane. This last process is the process we are most concerned about. The postsynaptic membrane is a lipid bilayer with interstitial fluid on the outside of the cell and cytoplasm on the inside of the cell. By binding to the binding site, the neurotransmitter opens the selectively permeable receptor, which will allow sodium to flow into the cell. This occurs because of 2 processes, osmosis and electrostatic pressure. Osmosis is when something flows against the concentration gradient. Because sodium is at a higher concentration outside of the cell, it will flow into the cell to create an equilibrium. Electrostatic pressure is a process built on the premise that opposites attract. Because the outside of the cell is positive and the inside of the cell is negative, sodium will flow into the cell in order to create an equilibrium. To look at this more closely, we can use the readings from an oscilloscope. Initially, when we started at the resting membrane potential, our reading was at -70 millivolts. If the processes of osmosis and electrostatic pressure occur, we can see a slight depolarization that reflects the increase of sodium into the cell. This slight depolarization is the excitatory postsynaptic potential. When sodium tries to reach equilibrium, multiple neurotransmitters bind to the binding sites on the ionotropic receptors selectively permeable to sodium, allowing a lot of sodium to flow into the cell, creating a temporal or spatial summation. When this temporal or spatial summation reaches the axon helix, it causes a threshold of excitation, which occurs at -65 millivolts. And that initiates the action potential. This collection at the axon helix causes voltage-gated channels to open. Unlike ionotropic receptors, these do not require the binding of a neurotransmitter. With this summation of sodium, there is a massive depolarization that occurs. When the oscilloscope reads at a positive 55 millivolts, sodium levels have reached their equilibrium. This now creates an imbalance of potassium inside of the cell. Because sodium is positive, potassium now wants to repel against the increased positive charge and flow out of the cell where it is more negatively charged and where potassium is less concentrated. This creates a massive hypolarization until potassium levels reach an equilibrium at -75 millivolts. Then the cell's potassium and sodium pumps bring the cell back to its resting membrane potential at -70 millivolts. This action potential does not occur just once. Instead, it flows down the shaft of the axon by jumping from nodes of Ranvier to nodes of Ranvier in an action called saltatory conduction. This occurs until it reaches the terminal button. In the terminal buttons, the action potential interacts with calcium, which enables vesicles to bind to the presynaptic membrane and empty new neurotransmitters into the synapse between cells B and cell C.